Hi everyone, this is the preview lecture for lecture 7 and we are today talking about the Newton-Raphson method. Up to now, up to lecture 6, we have discussed about Poisson equation. So, as a result of our discussion in lecture 6, now we understand if we have a low Vg value, then since we have a small electron density, therefore our assumption of depletion approximation can be easily justified. However, at the same time, we now understand if we have a high Vg value, then our electron density is quite high, so depletion approximation cannot be used any longer. Therefore, in general case, we have to solve the following equation. Epsilon equal to, now we have positive q and I exponential phi over Vt. This is a contribution from electrons, and also we have a similar contribution from holes, and here we have doping density. So now we understand this is the form of Poisson equation which is valid at the equilibrium condition. Then unfortunately, here right hand side we have the terms which is explicitly dependent on the electrostatic potential. For example, this term is really dependent on electrostatic potential. Also, this term is dependent on the electrostatic potential. So, when we consider it at equilibrium with the electron contribution and hole contribution, it becomes a non-linear equation. So, the Poisson equation at equilibrium written in this form frequently called as non-linear Poisson equation in computational microelectronics. But that does not mean that this equation, or the Gauss law, has changed in its nature at equilibrium. It is just a mathematical form of Poisson equation at equilibrium. Anyway, since the equation now becomes non-linear on the electrostatic potential, we have to find out how can we solve such a non-linear equation. That is the main topic of today's lecture. So in this lecture is devoted the powerful technique to solve the nonlinear equation. It is called Newton-Raphson method. Okay. So Newton method. So without starting from the theory, let me just start from a simple example. Let's say that we have to solve x square minus 1 equal to 0. This is our equation, and this is really a trivial equation. But anyhow, we have to solve it. If we have to solve it, the usual way is, of course, just say squared x equal to 1. After that, take the square root of left hand side and right hand side. We will get x equal to positive 1 or negative 1. This way was taught to you when you are in a younger age, and somebody told you that, okay, if you have such a kind of form, then you can just move this constant term into your right hand side. After that, you can take the square root of the entire term. That was taught by you, but in our numerical simulation, it is very difficult to understand this manipulation. So therefore, we need more general technique to solve this nonlinear equation. Then how can we do that? The solution is quite simple to human, but our aim is to find out a way which is accessible to our computer. So instead of following certain solution procedure due to certain intelligence being, we just arbitrarily assume a temporal solution x naught. If x naught is close to 1, then maybe we will say, oh, x naught is close to the solution. And if x naught is, for example, 10 to the 6, 1 million, then we will say maybe x naught is far away from the solution. Okay, so anyhow, it is up to our decision whether x naught is decided as 1.1 or 1 million. Anyway, we can set certain guess on the solution. So x naught can be an arbitrary guess. After that, we have to admit that this is not the solution. Why it is not the solution? Or why x naught, the real solution, is the solution? It is simply because when you insert your x naught into our original equation, then the solution satisfies the equality. But unfortunately, in the case of any guess, if it is not perfect, then you will get non-zero values when you evaluate the left-hand side of your equation. Our initial guess is not perfectly satisfy the equality. So that is our first step. Then we wanted to make it. So instead of that, let me just make a certain change. So instead of this unsuccessful equality, why don't you say we wanted to make it squared x1. Here x1 is more improved solution than x0. Then let's just say this happen to be x1 satisfies the equality. This is our hope. Then if this is really the case, then we can stop there. Okay, since x1 satisfies the equality, the x1, our x1 is the solution of this equation. Of course, still, there is no guarantee that this updated x1 satisfies this equality. Okay, now we say that still it is not satisfied by our x1. x1 is not the real solution. However, for example, think about this one. Previously, your initial guess was 10 to the 3. Then your left hand side evaluated one is just 10 to the 6 minus 1. Oh, that is a huge number. So stressed by this huge number, you just reduce it. For example, let's say you have now 10 to the 2. Then what will happen? In this case, you will have 10 to the 4 minus 1. This is quite large number still, but it is much better than almost 1 million. This is just 10,000, so 100 times better than the first one. And let's say that we are now moving to x2 by hoping that x2 is even better than x0 and x1. Then, yes. For example, if we say x2 equal to just 10, then what will happen? In this case, our left-hand side will be just 99. Oh, 99 is still a large number, but compared with other numbers, that shows remarkable improvement. If we just continue this step, x3 squared minus 1, that can be also away from the solution. But point is, by repeating this procedure, if we are in the right direction, then eventually we can approach to the realistic solution. In this Newton-Raphson method, usually we cannot arrive the exact solution. But in numerical sense, we can find arbitrarily close solution to the realistic solution. For example, after certain iteration, then now you have the values like x, your x, and after 100 iteration, now you have 1 plus just a small number epsilon. Oh, epsilon can be a very small number. Then, even in this case, when you evaluate it, the square of this number, that will be just 1 plus 2 epsilon plus epsilon square minus 1. So you will get 2 times epsilon plus epsilon square. Certainly, this cannot be 0. This is true. So still, your solution is slightly different from the real solution, the number 1. But let's say that epsilon is just 10 to the minus 14. Then what will happen? In this case, although your solution is not exactly 1, but in numeric sense, you will be satisfied with this number because it is quite close to the realistic solution. So I wanted to say this is the best thing we can expect from the Newton-Raphson method. So we do not have the analytic solution, but the solution where the left-hand side of our equation becomes really small, so close to the real solution. Now your goal is, yes, you have a certain temporal solution xn, but it is not good enough. So next time you wanted to introduce a better solution, xn plus 1. So because n plus 1's iteration, and you hope that this one satisfy the equality. That is your assertion. Although my xn is not the solution, but its successor xn minus 1 can satisfy the equality. That is our hope. Then how can we get the xn plus 1 which improve the situation? That's the trick. Although xn is not the solution, not a solution, and we assume that n plus 1 is a solution. So from this xn, how can we find out xn plus 1? In order to do that, we have introduced certain relation. Okay, we have xn, and by adding certain correction of x, then we will get the n plus 1. Instead of squared xn plus 1, I will just write it xn plus correction. So let's say this is just delta for simplicity, n squared minus 1 equal to 0. Although xn itself does not satisfy the left hand side equal to 0, but hope that by adding the correction or update delta, then this one really satisfies the equality. In order to satisfy this assertion, what we can do is just to solve it. How can you solve? So in this case, we treat delta as an unknown variable. Okay, in this case, we can just expand it, xn squared. You know, xn is already given number in this case, and 2 times xn delta and plus delta squared minus 1 equal to 0. Up to now, everything is just exact. But point is, very frequently, we assume that delta is regarded as a small quantity. Once we say delta can be regarded as a small quantity, then what will happen? It immediately say in this linear order, square of delta can be safely neglected in this case. It can be regarded as 0. So if we adopt this linear order approximation for delta, then now the equation becomes xn squared plus 2xn delta, and previously we had term corresponding to second order for delta, but that is now gone, and it becomes minus 1 equal to 0. When we make a comparison between this original form and this approximated form, linearly approximated form, the change seems to be trivial. But point is, you know, this one is nonlinear. And fortunately, this one is linear only because we have made a linearization. So then what is the consequence of this linear and non-linear differences? Since our linearized system is linear, then we can solve it. I mean that 2 times xn delta equal to minus xn squared minus 1. So now we can find that delta equal to xn squared minus 1 divided by 2 times xn, also having the global negative sign. Okay, so up to now, I'm just showing that when xn, our temporal solution, is not successful, by adding a small correction, we assert that this one satisfies the equation. After that, during the expansion, we introduce linearization. Then resultant linear system can be easily solved. Calculated delta cannot be an exact one. Although when you insert this delta into your equation, there is no guarantee that you actually satisfy the equation because you have already introduced linearization approximation. But one thing is, okay, although that is not a perfect way to find out the solution, but maybe this corrected version can be better than uncorrected version. When we make a comparison xn and xn plus delta, if xn plus delta gives you better result, then you should go to xn plus delta, the corrected solution. And from this corrected solution, you can repeat once again another correction, another correction, another correction. Eventually, when you have a quite small error in your equation. Let me give you a concrete example. Okay, so let's start to x not equal to number 2. This is number 2, then 2 minus 1 gives 3. This number 3 indicate that your solution x naught is not the solution. If this number is close to 0, then you have a better solution. If this number is even larger than number 3, then your solution is even worse. So I think that this number x squared minus 1 can be regarded as an indicator for the quality of your solution. Then, instead of x naught itself, now we introduce x naught plus delta x and just insert it. Then, when you insert this number into your equation, then you will have this form. You have already seen it before. And when you insert number 2 and number 2 here, you will have minus 3 divided by number 4. So your correction delta x should be minus 3/4. Okay, if we have calculated in exact way, the answer should be minus 1. If you find out the minus 1 directly, then everything will become perfect. So when you just insert minus 1, your next solution will be 1, and you will immediately find that 1 minus 1 becomes 0. So everybody is quite happy. But please note that that cannot be done because our system is nonlinear. However, this approximated or linearized system can be solved by us quite easily, although not perfect, but this is a really feasible way to get the update. And now say that your first correction becomes minus 3/4. Then your next trial should be 5/4, and it is already much closer to 1 than our original number 2. And once again, when we insert it, then you can find that your correction now becomes minus 9/40. Oh, yes. So this is already quite small. And now your updated solution now becomes 41/40. Please remember that you have started from number 2, and after one step, your number becomes 5/4. After one step further, now your solution becomes 41/40. Oh, it is rapidly approaching to number 1. So therefore, after spending more and more iteration for this type, then you can easily get quite a satisfying number for your problem. And of course, we have to ask one question. We have start from number 2, and eventually it is expected that we are approaching to number 1. And think about the case where we start from -2. Then is your solution approaching to 1 or -1? There are two different solutions, and what will happen to your solution? Please think about it. I have spent my time to explain the Newton method. There was only a single unknown variable and the equation was nonlinear. But in our case, in our Poisson equation, actually we have various unknown variables. I mean that if we have 10 grid points, then we have 10 unknown variables corresponding to 10 discrete points. If we have 100 grid points, then we have 100 unknown variables. Then we have to think about the solution for coupled nonlinear equation. Also, even in this case, instead of showing the theory, I wanted to start from a trivial example. In this case, you have 3 variables. For example, phi1, phi2, phi3. You can treat it as electrostatic potential at 3 different positions. So, in this case, you have evaluated your equation 1, 2, 3. A vector containing phi1, phi2, phi3 should satisfy this first equation and second equation and the last equation simultaneously. Let's say that you have a certain vector, solution vector having phi1, phi2, phi3, and your first and second equation are exactly satisfied. You have exactly zero number for your first and second equation. But say that your third equation failures significantly. Then my question is this trial vector can be a solution of your system or not? Obviously, it cannot be regarded as a solution. So therefore, our solution vector should satisfy all equations simultaneously. Please remember that when we have a single variable, or we selected a single number as an initial guess. So now we have a solution vector. So also we have to introduce an initial guess vector for our equations. Our solution phi1, phi2, phi3 should satisfy at everywhere. The first point and second point and third point should give you exactly 0, 0, and 0. However, at the first time or at the beginning of a solution procedure, there is no guarantee that we have the solution. So anyhow, we have to introduce a guess. Please note that previously we introduced a single number, but now we have to introduce a single vector. Okay, their entries are determined by yourself. You should carefully design the initial guess. But even when you carefully design this initial guess. Actually, when you evaluated F1, F2, and F3, then there is no guarantee that you have all 0, 0, 0 for everywhere. Your vector, R vector, or this is frequently called as residue vector. Initially, your initial guess cannot make the residue vector to a null vector. If this is really a null vector from the beginning, then you get the solution. Everything is done. So, hooray. But let's assume that your initial residue vector is not 0. So your goal is now make it null. Make it a null vector. So that is your goal. Previously, you wanted to make it 0 when you have a single variable. But since we are talking about a vector, then now we have to have null vector. Then the remaining procedure is quite similar with the previous one. Previously, we just introduce a correction or update to our solution. But since our solution is now phi 1, phi 2, and phi 3, therefore correction should be also attached to phi 1, phi 2, and phi 3. Each of them should be corrected. So now this is initial guess vector, and this can be called as correction vector, or more frequently update vector. Then our goal now reduced to just to calculate the update vector. What is the required update vector to improve our situation? That is now our goal. And let's just do it together with me. Here, instead of phi, the initial guess, we introduce correction. These corrections are added, and right now we have no idea of their values. Actually, we wanted to calculate their values. Then now, previously we had made something like this: x naught plus delta, which is exactly x naught squared times 2 x naught delta plus delta square, was approximated as x squared x naught plus 2 times x naught delta. So we have introduced linearization. F1 function takes 3 numbers, 1, 2, 3. So therefore, if we have introduced delta phi 1, then it can change. Also, when you introduce delta phi 2, it can introduce change. Also, when you introduce delta phi 3, that can also introduce changes in the value of phi 1 evaluated. But point is, since we have introduced the linearization step, so therefore we can safely say phi 1, phi 2, and phi 3, which is corresponding to all 0 delta phi's, and we can have delta phi 1, the linear term, and delta phi 2, the linear term, and delta phi 3, linear term, with respect to delta phi 1, delta phi 2, and delta phi 3. So what is the value required for this position? And what is the value required for this position? And what is value required for this position? you can easily understand that should be the partial derivative of your f1 function with respect to phi 1 in this case. In this case, your f1 with respect to phi 2. And finally, here you have your f1 with respect to phi 3. These partial derivatives are required. So, in this slide, I just showing the manipulated version. But why don't you just read the first law? The first law just looks like this. This one, f1 evaluated with our temporal solution, current solution. And now here we have a matrix vector multiplication. But since we are working with the first law, just to evaluate this multiplication, that will give you the first law of this vector. The first law is obtained by multiplying this partial derivative and delta phi 1, partial derivative delta phi 2, partial derivative and delta phi 3. This is exactly the one I have manually wrote in this case, in this part. So you can easily understand this form is a compact form for representing linearized version of our f1 function and f2 function and f3 function. Oh, and at the first glance, it looks quite complicated. However, when we have a look at the matrix, actually, we can find that every component is just given by delta f over round delta phi. The only different terms, their indexes here and there. We have two indexes. And if we have a first law, the component corresponding to first law have all 1, 1, 1. Second law has 2, 2, 2. Third law has 3, 3, and 3. So simply speaking, in this matrix, the component is simply given by law index f of given law index. And when you have a look at also this phi index, here we have 1, 1, 1 for first column, 2, 2, 2 for second column, and 3, 3, 3 for third column. So we can say that this is corresponding to column index. Although this matrix looks quite complicated, but if we call it as J matrix, let's say that we call it as a J matrix, and J I, J component is simply defined as round fi over round phi j. That is enough to specify this J matrix. You know its original name. Its name is Jacobian matrix. So Jacobian matrix occurs at the first time in our lecture. Jacobian plays a central role in our implementation. Okay. Up to now, we have introduced certain quantities. One, we have just introduced Jacobian matrix. And this red colored vector that contains updates of each variable it is quite natural to call it as the update vector. Then what is the remaining one? This is again a vector, and it contains the functions like f1, f2, and f3 with the initial guess, and we have already called it as a residue vector. So now we have residue vector. When I summarize it, then we can find quite a simplified view. This equation, seemingly quite complicated, can be written as residue vector plus Jacobian matrix times update vector should be 0. That is the consequence of our linearization. Then let me introduce a simple notation for this residue vector, Jacobian matrix, and update vector. How about this residue vector that is written as R, taking the first R, and Jacobian matrix is written as just J from Jacobian, and say this update vector is delta phi. Okay, now it becomes 0. So now we can say J times delta phi should be minus R, as shown here. So if we can solve this matrix vector equation, then for example by multiplying inverse of J, you can get delta phi equal to minus J inverse R. Then now you get the solution or get the update for your temporal solution. By using this update vector, then you can improve your solution. That is the way you can do. As you can see, now our Newton-Raphson method now becomes just taking the inverse of Jacobian matrix. So in order to evaluate Jacobian matrix times update vector equal to minus residue, first of all you have to evaluate Jacobian matrix itself. In this specific example, like yes, then why don't you just calculate it? So J 1,1 component is by definition round f1 over round phi 1. So when you have a look at this number, then what is the partial derivative with respect to phi 1? That does not contribute, and we have minus 2 from this term and exponential phi 1 from this term. That's it. And 1,2 component now becomes just number 1 because of this term. And J 1,3, there is no dependencies on phi 3, so it's gone. Following this way, you can evaluate all of matrix component for your Jacobian matrix. And that is done in our slide here. And you can see that this is the Jacobian matrix of our interest. So you can just implement it, and since this is so important, why don't you just read our MATLAB example together with me. First, our initial guess is arbitrarily chosen. For example, 1, 2, 3. There is no sophisticated guess on it. So 1, 2, 3, 3, 2, 1, anything. Yes, anything will not be a solution. There is no chance for us to get the solution immediately. Okay. After that, we can build the Jacobian matrix. Here you can see that minus 2 exponential phi 1 and 1, 0. That is exactly corresponding to minus 2 minus exponential 1, 1, 0. We are just typing our Jacobian matrix in it. Okay, so Jacobian matrix is done. This is corresponding to our J matrix. After that, we calculate the residue vector. And residue vector, what is it? This is corresponding to your F1, and this is F2, and this is F3. By inserting the current value phi 1 and phi 2 and phi 3, you can calculate it. Yes, now you have a Jacobian matrix and residue. What will happen? By just taking Jacobian matrix and backslash and residue vector and taking the minus sign, that will give you the update vector. So when you have a look at it, then your update vector simply given by Jacobian and inverse of Jacobian multiplied by minus residue vector. Then after you get this update, this is not the final. So this is just correction for your solution, and your solution should be updated with your update vector. And you can repeat it until your update becomes really small. Therefore, numerically, you are quite close to the solution. So the full code is here. Only difference is now you have introduced for loop. This is just 10 times for loops. More sophisticated or more advanced implementation will have a certain criterion to stop this loop. Whenever you have quite close to the real solution, then you don't have to waste your time. But in this trivial example, we just learn sufficient number of Newton iterations. After that, we get the solution. Well, our initial solution or initial guess was 1, 2, 3. Please remember it. And after learn this example, then you will find this number. Yes. So 1, 2, 3 was our initial guess, and we get this real solution. So of course, there is no chance for us happen to be have this solution from the beginning. So, well, even in this simple 3 unknown variable case, without the computer simulation or numerical analysis, it will be very difficult for us get the solution. Fortunately, we are living with quite much advanced computers, and we are quite lucky to have the solution. Okay, up to now, I have discussed about Newton iteration or Newton method. First, I have explained a single variable case. After that, I have expanded it to the multi-variable cases. Although the notation becomes complicated, however, the principle or underlying idea is the same, so you can easily understand. Well, now you have a quite simple homework. So in this case, we have only a single variable, and this is your equation, and this is your residue, so you should evaluate it. If you insert a certain number, obviously you will not have the solution. But when you introduce certain value close to your solution, then you will get the residue quite close to 0. In order to make it physical problem, so let's introduce some physical meaning on it. So this is our equation, and here n plus is interpreted as what? Interpreted as a doping density, positively ionized doping density. And this one is interpreted as your intrinsic carrier density. And this is interpreted as the summer voltage, and phi is obviously electrostatic potential. And assume the room temperature, so 300 Kelvin is assumed, and intrinsic carrier density is assumed to be 10 to 10 per cubic centimeter. Later you will have much better values, but for a while it's okay, please use it. Then now your goal is numerically solve this equation. Starting from certain initial guess, you should get the numerical solution for this equation. Please test your code for positive n plus value corresponding to your n type, and also test the same magnitude but negative values of n plus corresponding to p-type material. Its absolute value varies from 10 to 10 to 10 to the 18. Of course, you have an analytic solution, so compare your numerical result with the analytic solution. Okay, I think that's it for today's lecture, lecture 7, and see you Wednesday.